think we can start now. Hello, good morning to everyone. We're glad you're here attending to this Make Mode training. We will go through our mechanical mode characteristics for finding mechanical faults in different components, and we will just give some examples of its use. My name is David Gambarte. I will be delivering the webinar as a business developer for Asia Pacific at FLIR. And I will have my colleagues, Manula and Abraham, which are technical experts in our cameras in general, but also in mechanical faults. And they will be supporting me from the background and, of course, adding some information if it's needed during the webinar speech. I will start now. We have around 35 participants now online, which is fair enough. And I really thank you for being here. As I said before, please, if you have any questions along my presentation, add them into the chat. In the upper bar of the application, you will find a chat or Q&A as well if you want. But the chat is going to be our main communication channel, so you can add any questions there, any comments. And my colleagues will be replying to them along we are actually going on with the webinar. Yes, we are starting now at this very moment. Yes. So, as I said, welcome to a Make Mode training for the Si2 series. Yes, the content of this webinar is going to have one slide about why Make Mode, why we are actually going in this direction, how it works, the FLIR Si2 models with Make Mode. So we have two models actually that have the Make Mode included. Operating the Make Mode tips for a demo, and examples and case study. Why the Make Mode? So mechanical fault detection, discover mechanical issues before they lead to a costly and planned downtime. So why we need to find them is because we want actually to do predictive maintenance. We want to find them before they actually lead into a problem. So camera operation allows quick detection and measurement of bearing and other mechanical issues that can lead into cost of production disruptions or safety hazards. So basically, there are many consequences or many derivative consequences of having mechanical faults, and the camera will actually help you to find the faults before they actually lead into a problem, as we said before. How the Make Mode works, we find faulty bearings, rollers, gears, and other mechanical equipment that can generate vibration due to a variety of faults, some of which can transmit through the air and noise. And that's the way our camera is actually detecting them. Bearings and rollers in poor condition might produce grinding, squeezing, crackle, rumble, groan. So all other types of audible and ultrasonic noise sound, and those are actually detected by our camera. Si2 Make Mode measures mechanical noise in three ways. So we give you insights in three different ways, providing the decibels, so the sound pressure level. We provide you with kurtosis and the crest factors. And those in combinations and compare over time can actually give you information about the state of your components or your equipment. So the user has to select normal, high, or ultra modes, filter mode. So that basically means that we have three different filters that we have in other applications in the camera. And by playing with those filters, you will be able to find the best kind of way of, showing the data in a screen to be able to analyze what kind of fault you have. These are the two cameras that we have that include the mechanical mode. So we have the Si2 LD that has mechanical fault issues, as we said, and then we also have gas and compressor leak detection in the camera, and it's ideal for manufacturing industries or foreign industries where those mechanical faults or leaks can happen. And the Si2 Pro, which is actually having the already explained two modes plus the partial discharge detection and analytics in the camera. So the advantages, so we have like it's a great accessibility. So Si2 can identify faults in locations that are very difficult or unsafe to reach. Efficiency, so scanning is really easy and fast and covers a wide range of areas, enable quick fault detection without the need of installing any kind of like detection devices. And easy of use. As you know, if you're familiar with our cameras are well known by being extremely easy to use, and this is aligned with our kind of product philosophy. So mechanical fault works really easily, so you will find where there is a potential mechanical fault by just inspecting with the camera the areas where you suspect that there should be something or you might actually potentially have a problem, and the camera will actually spot where there are the mechanical faults without any kind of like a thorough manipulation or calculation. So you will just find where the mechanical faults are. We have a video, and unfortunately, we were actually checking the video right before the presentation, and it's not working the sound. So we will share with you the link of the video after this webinar, and you will be able to watch the video. So no problem about it, but I apologize that we cannot actually show the video because it's meaningless without the sound. So how we interpreted the key metrics that we are showing, like SPL, crest factor, and kurtosis. So SPL measures the sound strength and can be used to compare different bearings. A higher SPL can show poor bearing conditions. To be able to compare SPL, it should be compared against similar bearings measured at a similar distance. So basically, we need to give conditions that are actually comparable in order to compare different bearings in different situations. Crest factor indicates the ratio between the peak amplitude and the RMS value of the signal a signal. And a healthy bearing has a crest factor of less than 5. A value of 6 or above might indicate bearing faults. Kurtosis measures the sample distribution in the sound signal. A healthy bearing has a kurtosis of around 0. Values of 2 or above of kurtosis indicate bearing faults. It's recommended to compare the crest factor, kurtosis, and SPL of a bearing to healthy bearings of the same type. So basically, you will need to compare when you have like all the data from a potential fault. It will be recommended to compare it with healthy bearings in order to understand what are the conditions of this specific bearing fault. So the crest factor, quick and simple way to detect mechanical faults. Crest factor is a measure of a peak to RMS ratio of a signal and indicates the peakness or peakiness of the signal. A higher crest factor implies more peaks and spikes in the signal, indicating potential issues like mechanical impact or transient events. Changes in crest factor might signify changes in the mechanical condition of the system, such as bearing faults or gear impacts. Then now we move to kurtosis. Kurtosis is a statistical measure that quantifies the tileness or peakiness of a distribution. It measures the degree of which a distribution's data points are concentrated around the mean and the tail's thickness. This sounds fairly complex, we can actually reply into the chat questions later on or along the time if you are actually having any more questions. And I understand that this might actually need for you to play a little bit with the camera in order to understand, but we will actually try to help you as much as possible on this. Kurtosis indicates the distribution shape and the presence of outliers of extreme values. Positive kurtosis indicates a distribution with heavily tails and more extreme values, while negative kurtosis suggests a distribution with lighter tails and fewer extreme values. So this is just information about the kurtosis statistical term. Application cases. For example, faulty conveyor belts bearing, right? So observe the transportation belts, focus on the moving rollers elements, the camera targets noise-producing elements, pay special attention to locations with bearings, as these are the critical areas, and monitor the SPL, as we said, kurtosis and crest factor that will be actually shown on screen while you are actually inspecting. Locations to inspect. From our experience, naturally, you might actually find other uses, but this is what we actually so far have in our own experience, and we can actually say that camera is working well for these uses. Conveyor belts, transporters, motors, fans, pump, compressor bearings, and base, mechanical couplings, gearboxes, pulleys, and of course, on any other mechanical elements. Practical tips. We're going to go through these as we explained already before some of this information. If there are typical mechanical elements, always compare them to SPL, crest factor, and kurtosis. Yes, to compare mechanical elements where you find like a potential fault with the camera with other potential healthy elements that are similar to it. If you can find similar elements to compare, look for high crest factors and kurtosis that indicate the possible faults, of course. Maintain the same distance and keep the same filter mode when taking a snapshot for comparison with similar mechanical elements. Consider scanning section by section when examining a larger area, such as a long conveyor belt. So yes, go section by section. Use the zoom feature to isolate distracting sound sources if needed. Wait until the crest factor and kurtosis values stabilize before taking the snapshot. This should take about 4 seconds. So wait a little bit, and then you will get the right, the right information on the screen. Look for mechanical issues that are exceptionally loud. High SPL a standard distance, have a crest factor of 6 or more, and kurtosis value 2 or more. So this is actually going again over the same topic that we mentioned before. This should be flagged for further investigation. Naturally, we don't give you exactly the kind of the evaluation of the mechanical fault. We give you information for further investigation where you need to understand what components you have in your own facilities. Quicker for further analysis. So comparison approach, time trend approach, and direct approach. So we can maybe summarize that these are the 2 different approaches for getting the analytics or analysis with our make mode in cameras. So the direct approach, quantitative direct approach, so use SPL, crest factor, and kurtosis values to identify faults. Example, as we said, more than 6 or more than 6 kurtosis, more than 2 unsignificant elevated SPLs should indicate a possible mechanical fault. Sorry, it's not 6 or more than 6, it's more than 6 and more than 2. So to correct myself. Qualitative approach, identify locations, components which are not intended to be a strongest sound source in the frame. Example, if a mechanical couple is identified as the strongest sound source in the snapshot, instead of the motor or pump, this will indicate that the possible abnormality is in the coupler. So of course, as it happens with any other kind of solutions, we need to apply the common sense. and understanding the nature of the different components that we are inspecting. Comparison approach. Ensure the camera is in mechanical mode. Naturally, this is very important, and this applies to all the different inspections that you are performing. Select the normal filter and single source mode. Point the camera towards the area in which mechanical elements are present. Hold the camera steadily and try to get a stable sound map. The camera will show the strongest sound source on the screen. Use FPL, crest factor, and kurtosis to compare different elements, as we mentioned. Distance, angle, and same type of components are important factors to take into account. This is as easy as it is, as we are showing it now. So that's why we say that our approach is pretty easy to use cameras, easy to use solutions. Then naturally, you need to actually make your own decisions when you are inspecting your own elements, but we provide you with the data for it. The trend approach or time trend approach. Take a snapshot similar to the comparison method. Utilize SPL, crest factor, and kurtosis again in time trending to predict abnormal behaviors. So try to predict what is going to happen, like by doing a time trend approach, different analysis along the time. Establish baseline values for SPL, crest factor, and kurtosis by averaging values during normal equipment operation. Use these baseline values as reference points for assessing equipment health and preparing lubrication schedules. So yes, comparison along the time is extremely important. So you can actually, if you can perform inspections every, I don't know, in weekly basis, in bi-weekly basis, in monthly basis, you will actually get a lot of valuable information about your equipment. Examples. This is a burning example. So27 approach, quantitative, you have a high SPL in this case, a crest factor of 27.78, and a kurtosis of 49.66. And of course, the SPL is high as well. So this is a clear mechanical fault in a bearing. And this doesn't require any kind of time trend comparison. So you just can actually go and inspect because there's something to inspect there. This is a bit more complex analysis. So we have a mechanical copper here. As you can see, the copper, the fault is found in the copper area. And this is also direct approach. So the high SPL is shown in here is 37.3. As you can see in the screen in the upper side, the left upper side of the screen, and then the crest factor is slightly over 6, and kurtosis is over 2. So mechanical coppers in condition do not make any sound. In this case, the failure is more evident as it produces acoustic emissions. So this is a very clear case, and this might be a very valuable use for the cameras. So faulty impact rollers. This is here we recommend the comparison approach. So in the image we can see two rollers. One is in good condition and the other one is showing an acoustic image over the bearing area. So it's very clear that one is in good condition, the other one, the camera is showing that there is something to inspect. Based on this comparison, we can suspect that there is an issue. Of course, you need to inspect, you need to check yourself. Sometimes other sound sources might appear in the image. It is important to pay attention to the location of the sound block when determining whether it is bearing fault or not. So, as we said, we always recommend for further inspection when you find, a potential fault with the camera. So, another mechanical copper here. So, direct approach again. The FLIR Si2 acoustic camera was used for inspection in mechanical work in metal working facilities, where mechanical equipment is used in various stages of the manufacturing process. The Si2 quickly confirmed suspicions about known issues. So they already knew that there was something going on there. The camera helped to actually verify those and uncovered and severed previously unknown fault that led to a drive coupling failure between an electric motor and a pump just a few days after the inspection. So, this sometimes happens. You find something when performing a customer visit, and then there is something, a problem like being represented or being happening after a few days or a few weeks. So it's always good to go for further inspection when the camera is showing that there is something. Utilizing the decision support provided by the Si2 acoustic camera plan was immediately put in place for replace various chains and bearings to prevent further damage. So of course, here is where your expertise and you know how it comes into play. So you need to actually understand what to do and make your own decisions. We will provide you with all the data that we can to get the best decisions possible with the insights that we are providing to you. Note that in this case, the comparison method cannot be applied since the camera took a snapshot near to the motor. To make a fair comparison, the snapshot should be taken depicting in equal distance all the elements that we want to compare. So yes, always take into account distance, angles, when you want to compare similar elements, okay? So now we are getting to the end. This was pretty fast. So we have a lot of potential industries for this use, but this is just a list. We know that there are many other industries or applications where the camera can be used. These are some of them. So automate logistics centers and live platforms, like for example Amazon postal and paper services such as UPS, FedEx, etc. So these are just examples, of course. Cement production, mining, textile production, printing companies, electronic manufacturing, metal, paper, and plastic processing, food and beverage production. Most of the industries are also potential for LD detection. We in the same cameras where we have the mechanical. Just remember that we also have the leak detection for gases and for compressor. So the cameras are really complete and holistic solution for this kind of customers. Oops, sorry. This was completely my fault. So we went pretty fast. It was actually on purpose. We wanted to go fast over the slideshow. And now we will check if there are any further questions. I will try to reply them verbally together with my colleagues, Manula and Abraham. And then, of course, we can also be writing in the chat. I would like to thank to everyone that has been participating in this. We try to have it really kind of dynamic and fluent. We did a short presentation. We talk about the typical uses of the camera. We got your questions. We actually taking notes of your very valuable questions. We really thank for it. I will also thank to Manula, Abraham, and also Sue, that is the one who actually make this possible, because she actually organizes everything and coordinates everything and makes possible that we are here doing this webinar for you. And of course, thank you for your time. It took 1 hour. I hope it was valuable for you. And we will keep this record and share it with everyone, in the near future. So thank you very much for this, and I hope you have a really good day. Thank you.